Hi, in this video, we're going to have a quick discussion about oxidation process. Uh, in semiconductor fabrication process, oxidation is really important to isolate from the N FETs and P FETs, like between these. Without any isolation process, the the NMOS and PMOS will have an internal NPN or PNP transistors to make a latch structure. This will make the turning on or turning off the MOSFETs even harder, much harder than in the theory. Uh, in the in the old fabrication process, there was a local oxidation of silicon where low-cost processors were widely used. This is to with opening the region with lithography process and have an oxidation process to grow up the oxide layer and and this is the locally oxidized silicon. because the because the surface is wider than in the last part, the structure is called the bird's beak because the oxide layer is thicker than on the others. However, to make a deep oxide layer, we must make a a rather really wide area to be oxidized, and this does not help the define the bottom semiconductor process. So this low-cost fabrication process is not widely used in nowadays. Otherwise, this is the widely used process nowadays. Uh, this is the trench oxidation process. This is because we make a deep trench with for example, the deep reactive ion etching process we have discussed discussed before, and we put some oxide inside, or sometimes we also put some polysilicon inside to in some case. With this, we can keep the areas fully uh, separated and without consuming too much area. And this is how we planarize the surface of the semiconductor. We call this chemical mechanical polishing or planarization. This is the chemical is because of the slurry, because this slurry solution is kind of mixture with the chemicals that eradicate the unwanted material and a little bit of polishing materials to polish off the surface with the polishing brush with this spinning polishing brush. To to oxidize the materials, we use some kinds of oxidation process. Uh, Normally, the thermal oxidation process is widely used. This is because we can grow up the silicon with the heat and and the oxidation with the oxidizing materials such as uh, oxygen gas or H2O gas. Uh, Even though there are kind of modern oxide layers that can insulate the materials, but still the silicon oxide is a great insulator because the band gap is 9 electron volt so this can resist the really high electric electric you say the electric field. The process of oxidation is split up to two processes. One is dry oxidation with silicon with oxygen gas, and wet oxidation with silicon and vapor, uh, in specific water vapor. With oxidizing the silicon, the growing up portion is like 54%, and the consuming down is around 46%. In oxidation process, the oxidizing gas or humidity diffuses through the oxide and bake a coupling chemistry under in the oxide in the oxide and silicon substrate layer between layers. This is a brief. This is the oxidation bottling bottles. This means the the flux, the particle comes through the oxide is is the the initial particle numbers, the difference between the oxidation particles between the layer between oxide and silicon and the entrance of oxide divided by the length of the thickness of oxide with diffusion coefficient. If the initially without with in the beginning part of the oxidation, because there's no oxide layer, we can also put this initial number with the Ks, the surface rate constant. With these two formulas, we can draw a plot in the linear on the at the beginning point and parabolic on after the beginnings. There are some factors that influences oxidation rate. One is the dry and wet oxidation with the temperatures. The higher the temperatures, the rate of the oxidation is faster. And even the ambient pressure and the substrate toppings and so on, they also influence the rate of oxidation. For example, if the ambient pressure gets higher, even though the temperature is fixed, the oxidation rate is faster. This is sometimes used to that the high temperature in the normal oxidation cannot be used because normally the oxidation occurs in around 900 to 1000 degrees Celsius, but in some cases we cannot use this high temperature with this in this time. Because of this, we put more pressure than the normal, and we can cut down the temperature. And moreover, with the with these crystalline structures, because the bondings of the crystal is different different between the the planar or the kinds of orientations. And even though I'm going to tell you later, but the doping of the substrates also influences. Before I tell you about the oxidation in depth, I'm going to briefly tell you about the chlorine contain with the chlorine gas. Uh, because even though we put the oxidation in a clean room, but though some particles or the impurities can be left inside, so we put around 1 to 5% of hydrogen chloride gas into oxidizing gas such as O2 or water vapor. With this, the the chlorine gas puts the unwanted particle and gets out. So this can reduce the contaminations. This is this in this graph we can see the influences with dopants. Some dopants tend to live in silicon rather than oxide, and some other dopants want to stay in the oxide rather than silicon. With this case, uh, in this graph, the dopant tends to stay in the oxide rather than the silicon. So some dopants in the silicon moves into oxide, and in some dopants over there, this on the surface is kind of moving out of the oxide. Uh, on the other hand, with this is when the same thing happens in faster diffusion in the fast oxidation. The 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 dopants in the silicon is more get out of the silicon, but even in the silicon, even more dopants are moved out of the oxide. On the other hand, as you can see, the dopants over here, it tends to stay in the silicon rather than in the oxide. In, in slowly diffusing oxide into silicon, most of the dopants stay in this layer between silicon and oxide. Same thing happens, but when we grow the oxide even faster, some silicons some silicons move inside the silicon, and dopants in the oxide is nearly zero. When growing silicons, even though most of the modern silicon devices are made in the metal gate rather than polysilicon gate, but with polysilicon gates such as memory devices or flash memories, we still put polysilicon as gate because the grain boundaries, the oxidation is faster uh, on the boundaries rather than on the planes. The roughness of the surface increases when oxidized. Last but not least, let's talk about the topographical effect. Uh, when we make a hole when we make a hole with such as lithography and grow the silicon, because there is no oxide layer and there is oxide between around the hole, the growth of silicon is faster over here rather than over there. With this, with this, because of this, the consumed silicon is much deeper in this area rather than on this side. Thank you for listening.